Yo estoy de moderador esta mañana y vamos a presentar a mi querido amigo Aubrey de Grey. Le conozco de hace 25 años y es un orgullo tenerle acá, Aubrey. Y cambiamos de pantalla. Vamos a hacer traducción a través de Microsoft PowerPoint. Vamos a ver cómo funciona. Igual, su inglés es bueno. Everything ready. You can go.
20 minutes, right?
Yes.
Okay. Well, good morning, everybody. It is fantastic to be in this beautiful auditorium, and I am very grateful to my friend Jose Luis Cordero for inviting me here. I see that the subtitles are working, so let us hope for the best with you being able to understand everything I say. I apologize that I do not know any Spanish. So, I will speak today about the work that we are doing at LEV Foundation. Before that, though, I will give a little bit of background because I know that many people here are not biologists and are new to this field. Next slide, please. So I always begin with this question, which I believe is too often ignored. It's the fundamental question of our field. Why is aging so hard to defeat with medicine? 200 years ago, more than 1/3 of babies would die before the age of 1, even in the wealthiest countries in the world. And of course, now they don't. Even in the poorest countries in the world, not very many babies die very young. In fact, every single country in the world today has an average lifespan more than 50. Even in sub-Saharan Africa, aging is the biggest medical problem today. Now, so let us ask this question. What is so difficult about the health problems, the diseases of late life that makes them resistant to the methods that we have used so successfully for the diseases of early life? Next slide, please. Well, I think that this is the answer. We, of course, have machines like this that are much older than they were designed to live. This car was probably designed to last 10 or 15 years, but here it is. It's more than 100 years old, and it's working just as well as the day it was built. And it got that way because of preventative maintenance. It has been owned by people who wanted it to keep going, and they just did more thorough preventative maintenance on it than most of us do with our cars. So why is that relevant to the question on the previous slide? Well, simply because the human body is also a machine. Of course, it's a ridiculously, viciously complicated machine, but it's still a machine. And that means that its function is determined by its structure and composition. So that means that just as preventative maintenance works so well for simple man-made machines, it should also work in principle for the human body. Next slide, please. So this is another way of saying what I just said. At the bottom, I have a definition of aging. Now, aging is, it has been the major preoccupation of humanity since the beginning of civilization. So it's a bit embarrassing that we have so many different, pet definitions of aging. But this is the one that I like because it demystifies aging. It explains that aging really is something that we do fundamentally understand. Aging consists of the two processes that you are seeing at the bottom of this slide. First of all, there is a process going on throughout life whereby our metabolism generates accumulating damage in the body. Metabolism simply means the entire network of processes that keep us alive from one day to the next, and damage is the word that I use for the changes that metabolism causes to the molecular and cellular structure of the body. The reason I call these things damage is because the body is built to tolerate a certain amount of those changes, but only a certain amount. And eventually, there is too much, and that's when the right-hand process begins, where that damage creates and pushes forward the chronic, progressive conditions of late life that impair our physical function and our mental function and eventually kill us. So, the reason why that definition is useful is not just because it's easy to understand, even for people who are completely new to this field, but also because it helps us to distinguish the ways in which we might do something about aging. Now, if we go back to my first slide and the question, what's so different about age-related ill health versus early life ill health, then we can see that the way that we mostly try to attack the health problems of late life, the pathologies, is by what I'm calling here the geriatric approach. We completely ignore the fact that the health problems of late life are a side effect of being alive, whereas the health problems of early life are typically infections. And we try to attack, we wait until someone gets sick, and then we try to attack that sickness. And of course, just from looking at this simple picture, you can see why that has completely failed. Since the pathologies of late life are the consequences of something that's accumulating, the damage, it's more or less by definition that the attempts to attack those pathologies will become progressively less effective as time goes on. Now, I am not the first person to point this out. More than 100 years ago, a few people started to realize what I have just said, and that's where the whole field of gerontology came from. People said, well, look, we've got to be more preventative. Instead of trying to separate metabolism from pathology by separating damage from pathology, which is essentially the geriatrics approach, let's do it by separating metabolism from damage. Let's try to make the body run more cleanly. And the inspiration, of course, was the living world. We see a huge variation between different species in terms of the rate of aging. So people said, well, maybe we can try to understand the basis for those differences, that variation, and then we can use that understanding to create medicines that work. And that has also been completely unsuccessful, essentially because the creation of damage is just too intrinsically intertwined with the things that we need metabolism to do to keep us alive. So we just can't disentangle them. Metabolism is going to create damage, whether we like it or not. So the question is, do we have another option? And by about the 1970s, most people who studied aging had decided, no, we might as well give up and just, try to keep people as happy as we can as they sink into sickness and death. And if you were writing a grant application back then, it was completely impossible even to mention the idea of doing anything about aging. But in fact, there is a third approach, and it comes back to that car I just showed you. Preventative maintenance is the thing in the middle there. We say, let's just accept that metabolism is going to create damage, and let's not try to slow that down. And let's also accept that when there's too much damage, we're going to get sick. But let us separate those two processes from each other by periodically repairing some of that damage every so often, so that we never get too much damage, even though damage is constantly being created. That's what we do with cars, and it should work just as well with human beings. Next slide, please. So this is what it comes down to. I apologize that the colors are a little bit difficult to read, but 20 or more years ago, I thought about this way of attacking aging, and I realized that we could classify the many types of damage that the body does to itself into a relatively small number of categories. And my classification has a particular purpose. It's not just to make it easier to think about. It's also to make it easier to do something about. Because what we can do with this particular classification is we can, for each category, identify a generic approach to repairing it, to doing the maintenance that I was talking about a moment ago. So here is the list of ways that I suggested back then. And the good news is that now we have made so much progress on all of these things that they are being pursued in companies, in the private sector. In other words, they are being funded by people who are interested in earning money, in making money from these things. So that means they must be fairly near to actually working. Furthermore, for each of these categories, there is now at least a couple of other ways to do the same kind of thing, to repair the particular category of damage. So we have a lot of options now, and that is why I am pretty optimistic that we will make this all work pretty soon, in the next 12 to 15 years, with at least 50% probability. Furthermore, even though this idea, this way of thinking about attacking aging was very controversial 20 or more years ago when I first put it forward, it is no longer controversial. And honestly, I have our next speaker, Maria Blasco, to thank for that, because together with 4 colleagues, she wrote a paper called The Hallmarks of Aging, which was published in 2013, about 10 years after my paper, and which legitimized all of this. Essentially, it said, yes, we should think about aging as a collection of several different types of process, different types of damage, with different approaches to repairing them. So it's very gratifying that that is now a mainstream concept. Next slide, please. So what are we doing at LEV Foundation? Well, I don't have long, so I'm going to go through this rather quickly. But essentially, what we're doing is we are trying to extend the healthy lifespan of mice, starting when the mice are already in middle age, and we are doing it by the methods that I have just described. We are taking a lot of different treatments that will repair different types of damage in the bodies of these mice, and we are applying them all to the same mice at the same time and trying to get synergy, additivity, to get the mice to live longer with all of the treatments than they would with any one treatment on its own. And we are only currently doing one such experiment, but there is a huge need to do many more experiments like this. Nevertheless, the first experiment started early last year, and so it's nearly done. These mice live about 2.5 years on average, and we started when the mice were 1.5 years old. So we are trying to make them live longer. In the past, people who have tried to do this by simpler approaches have been able to extend the lifespan of mice by 3 or 4 months, starting at that age. Our ultimate goal is to do 3 times better than that, to get them to live about a year longer than they normally would. So next slide, please. So what are we doing? Next slide, please. This is basically what we're doing, as I've just said. We are combining a bunch of damage repair interventions, and we are starting in middle age. Next slide, please. So the key thing is we are not playing tricks. We are not trying to make it easy for ourselves by, for example, using mice that are impaired and that get old unusually rapidly. We are using normal mice. We are, of course, using repair approaches that try to be as different as possible from each other, repairing different types of damage. Next slide, please. And this is the overall design of our study. As you can see, it's a big study. We have 10 different treatment groups because we have 4 different interventions. So we are testing, we have a group that's getting all 4 of the interventions and a group that's not getting any of them. But we also have groups that are getting just one of them, so as to be able to validate that we are doing the experiment correctly. And we also have groups that are getting all but one of the interventions, so that we can identify cases where they cancel each other out. This is a big risk in any combination experiment like this. As you can see on the left, we are doing a lot of things to monitor the health of these mice, not just how long they live. Excuse me. We are looking at how old they look. We are looking at their behavior, whether they have good, how their memory is working, how their agility is working, how their strength is working. We are looking at their blood to do things like glucose tolerance. And we are also collecting tissues from these mice so as to test which parts of their bodies are aging more rapidly and less rapidly. We are killing some of the mice, sacrificing them at particular points on the survival curve, as you can see on the left, on the right. And all of this is in progress right now. Next slide, please. So it's huge, this experiment. You can see the numbers. We started with 1,000 mice, and we are storing more than 10,000 organs. We are doing hundreds of necropsies. We have, thousands of results per test. Next slide, please. And so these are the things we are doing. We have one intervention which is not really damage repair. It is more like something that makes the bodies of the mice think that they are in a famine and not getting enough food. That's a drug called rapamycin. But the other 3 interventions are repairing different types of damage. We are replacing some of the stem cells in the blood, in the bone marrow of these mice, with bone marrow stem cells taken from young mice. We are giving them something called a senolytic, which is a drug that kills senescent cells, cells that are accumulating in the body and are poisoning the body, but the body is failing to get rid of them. And we are using a particular approach that was developed by a very prominent researcher in Spain named Manuel Serrano. He found a very clever way to make a particular senolytic called navitoclax less toxic, and we are doing it that way. And then finally, we are doing something which, again, is pioneered by the next speaker, Dr. Maria Blasco. We are giving these mice gene therapy for a gene called telomerase. This is something that Maria showed maybe 10 years ago could extend the lifespan of normal mice, just like the other therapies. So these are the things. Next slide, please. And yeah, this is what I've told you already, the structure of the study. Next slide, please. And this is where we are. As I told you, the study began early last year. And we started when the mice were 18 months, 1.5 years old. So they are well past their average lifespan now. But we are showing a very clear result that the study is working. As you can see, the study looks a bit different if you look at males versus females. The thick lines, the blue one and the red one, are the big story. The blue line is the mice that are getting no intervention, and the red line is the mice that are getting all four. And as you can see, in both sexes, the mice that are getting all four are doing better than any of the other treatment groups. In the female mice, most of the benefit is coming from rapamycin. And that tells us that our damage repair interventions are working individually. We can see that from the other lines in the graph, but they are not covering all the bases. There are some things that are still killing these mice, even though some of the damage is being repaired. In the males, however, we have a very different story. The rapamycin is only giving about half of the benefit, if that. And the rest of the benefit seems to be coming from the damage repair interventions. We have not done rigorous statistical analysis on these curves yet, because we need to wait until all the mice have died. And as things stand, it looks like that will not be for another 4 or 6 months or so. So watch this space, as they say. But we are very happy that even though we are certainly not getting our goal of a whole year of life extension for these mice, nevertheless, we have strongly, unequivocally validated the concept that studies like this will give us the information to get to that point quickly. I firmly believe that studies of this nature are, at this point in the history of gerontology research, they are the most valuable studies that anybody could do. They will give more information per dollar spent on the study than any other experiment. And that's despite the fact that they're very expensive experiments. This experiment cost about $3.5 million already, and there's some of it still not done yet. But yet, the amount of information is so big that we believe we absolutely must get more of these studies done. It's very difficult to obtain the money to do them, because these studies do not generate new intellectual property, so the private sector is not very interested. And it's also very difficult to fit these studies into the normal academic funding structure, because nearly all the money needs to be spent right at the beginning of the experiment. But that's why I'm doing it, because my organization is funded entirely by philanthropy, by people giving us money even though they know that they're not going to get any of it back. Next slide, please. So this is just the takeaway that I've already told you. We need far more of these studies, not just with different interventions, we have plenty of those to test, but also with the same interventions at different doses. We've had to guess a lot with these studies. Next slide, please. So stay tuned. There will be more about this coming out in the next few months. And we have already described and put on our website the design that we currently have for the next study. We may revise it over the coming months because new results are constantly appearing from other laboratories around the world, but that's what we have at the moment. Next slide. There you go. So for those of you in the audience who want to get deeper into the science, I recommend the review paper that we wrote a few months ago in top journal in the field, describing all the details and motivation for the study. And if you want to help us do the next study as soon as possible, there's a QR code to help us to put together the funding that will be required. Thank you very much.